So my talk is titled, I think, Transitioning the AI capabilities from the clouds to the edge. So to that end, I'll present the AI solutions that we have and what they can do. So my name is Pierre Guiglion, and I'm a technical marketing engineer at ST. So we'll go through Edge AI in general, but I'll skip quickly through this because I want really to focus on the AI part, on the solutions. We'll introduce some context, introduce the main solution, NanoEdge AI, and look into some use cases. So just summary of the hardware parts that we provide at ST. So there's a whole ecosystem for every use case, pretty much. But here I would only like to focus on the yellow square here, the STM32N6, which is a microcontroller with a dedicated neural processing unit. So if you've got use cases that require some kind of parallelization for running heavy neural networks. So this will provide you with the ability on a microcontroller to have the same performances as for with a microprocessor, and for a fraction of the cost and for a fraction of the power consumption. So just very quickly. Okay, now a few things about Edge AI. So really this need for Edge AI comes from the quest for an ever smarter infrastructure, right? So today we are in an era where for the first time we can directly put intelligence in our devices, and pretty much any device. So there's many ways to distribute AI. And by the way, I keep saying AI, but really you should understand machine learning, right? So we can leverage the cloud, of course. That's the traditional way to do machine learning on the cloud. And then there's several flavors of the edge, right? It can come very locally, where there's billions of devices. So at the bottom here, really have the ability to place intelligence exactly where the signal from the sensors transform into data. So that's what I will be calling the edge. But there's also like edge nodes in the middle here with IoT gateways and micro data centers. All right. So why do we want to put intelligence into our devices? Well, because I think that many devices could be a bit more autonomous. For example, for predictive maintenance, it's quite a big use case. If we have a pump or a motor or any rotating machine, we want to be able to tell in advance if it's going to break down, right? And we want to act before it does. And especially the device could autonomously on its own trigger some reactions and so on without technicians having to do something directly. Same for home maintenance. So a dishwasher, for example, we'd like to know when to change some parts before they start breaking down. Also, security, if we want to classify maybe some different sound events, like a window breaking or a baby crying, or things like that. Also, people counting, so now you can take a simple time-of-flight sensor, place it somewhere on the ceiling, and just by placing a tiny machine learning library inside, figure out if one person is entering or exiting and so on. So you can really place this kind of intelligence now in any device. Okay, so just to clarify the difference between machine learning and traditional programming, really the strength of machine learning is that it really emulates the human way to learn. It learns through example. So we provide signal examples, like real data, real world data, and then the model learns from it. So it makes it very adaptable compared to standard programming, where most of the time it's a fixed logic that is not very flexible, usually. So if something changes in standard programming, we would need to rewrite algorithms, whereas in machine learning, we can just learn a bit more. So today there's much hype around AI, of course. Here, if we look at the Gartner hype cycle, this is 2021. we're really at the top of the hype here. And it creates lots of confusion because everyone's interested in AI, and many people think it's like magic, right? They know that they need AI, but they're not quite sure why. And this is why some companies really struggle to assign a realistic value to this AI or machine learning. But now we are starting to go down the slope here. Like the hype is starting to fade, and so we're starting to have real business opportunities. And in 2 to 5 years, the market will be ripe. So for most companies who want to develop some ML capabilities and put them into their devices, there's quite a few challenges, right? So you need tons of data, usually, and this data needs to be qualified. Then also to treat this data, there's a lack of data scientists. Usually data scientists, machine learning experts, they are quite expensive and are hard to come by. And also the way it works traditionally is that you train using all this data, you train very computationally expensive models on the cloud, which can take from a few days to a few weeks. And so it takes a lot of memory, takes lots of RAM, and also lots of energy. And all that represents quite a heavy upfront investment in terms of time, energy, so money. There's many frameworks that exist out there to do these kinds of things, like TensorFlow, scikit-learn, Keras. That are nice and are powerful, effective, but none of them today can do embedded learning. And what I mean by that is train a model from scratch from within the microcontroller. So this is where we introduce our AI solutions at ST. So mainly they come into 2 flavors. We've got the first one, which is based on Cube AI, STM32 Cube AI. So it starts here at this 3rd step. So before this 3rd step where you implement your model, first there's of course data preparation. You need to log data, you need to collect it and process it. And then you need to make a model from scratch. So if you have some machine learning expertise and you know how to design your neural network, you have the data and so on, this is a great way to go. So your model is the input for Cube AI, and then Cube AI optimizes it to fit within the constraints of a microcontroller, right? In terms of RAM, in terms of flash, and you can really allocate the memory and so on. And you can quantize also. So that's the traditional approach, let's say. And then you've got an alternative approach with NanoEdge AI, which is what I'm going to focus on today. And here, really, it's a tool that automates the whole process. So for an embedded developer who doesn't necessarily have expertise in machine learning, it's a very nice way to do all these things, and even includes now some data logging tools. So with NanoEdge, you can log some data, you can create your input data sets, then click a few buttons, and it will find for you the best model, which is step 2 here. So we'll find not only the best model, but the best shape for this model and the best pre-processing for your signal. And then you can test that this library, this model actually solves your problems, and then deploy it on the field on any STM32 microcontroller. So really, if I compare these 2 approaches, the one on the left, Cube AI, is more traditional. It's free of charge, of course. It's part of the AI ST ecosystem. Application agnostic, really, it works well for everything image related, or to treat video, or to do speech recognition, things like that. On the other side, NanoEdge, it's more, it works for any sensor, really, like accelerometer, temperature, pressure, current, voltage, or time of flight, or a combination of these. Anything that is not too consuming for the microcontroller, like, for example, we would avoid image or speech. So this NanoEdge really introduces an an automated way to find the best machine learning library for a given application out of millions of possible combinations. So it's really easy to use and shortens the development time by a big factor. One other thing is that there's no cloud dependency, so you can totally imagine having a device that is completely isolated from the outside world, that works on battery, for example, for a few years, and then does some learning and some inference and maybe some reporting or blinks LED to send alerts. And what is great also is that it works with existing hardware. So if you've got a device that already exists with many sensors and you would like to introduce some smart features meaning maybe being able to learn a state and to compare any other state with what you've learned. So that would be anomaly detection or classification. Yeah, if you have a few predetermined classes, you want to distinguish among them, you can do that as well. Or finally, regression. So regression, whenever you want to estimate a number, when your target is not a binary class, but rather a number. For example, you've got a motor, you've got the input current for the motor, and you're trying to estimate the rotation speed. So that would be an example. So now, how does it work? Okay, so in NanoEdge, before I go to how it works, we have 4 different types of projects that I've just mentioned. So the first one, anomaly detection, and then mainly n-class classification and extrapolation. So what is really unique about anomaly detection is that it provides the ability to do embedded learning, which means that you can place the library, the same library, on a fleet of, let's say, motors or pumps that are the same, that are supposed to be the same, but in practice, they are never exactly the same. So maybe some devices will have aged a bit more than others, and their behaviors will be different, or maybe their environmental conditions are not the same. So you need to account for that, and it's very difficult usually to do it with a static model. So here, with the embedded learning, you have the same library running on many different motors, and each one of them will gather their own specific knowledge and answer to the specific behavior of each machine, which is something really unique today. And the models that allow to do this were developed in-house by ST. Okay, so the idea is to, in order to find these AI libraries, is to use NanoEdge AI Studio. So NanoEdge AI Studio is a tool that runs on your PC, and it's like a search engine. So you provide it with some input data, then it searches for the best, not only type of machine learning model, but also the hyperparameters, so the shape of this model, and also preprocessing. So preprocessing can be FFT, if you need to look at the frequencies, can be like PCA, if not all your input parameters are important, but just a subset of them, or it can be reframing, standardizing, many different things. So all those building blocks will be automatically searched during the process. And then you get the library that you can embed into all your devices. Okay. Classification, quite self-explanatory. Okay, so let me show you how it works in practice. So this one is a demo. Actually, it's the same that we have on the ST pod. I don't know if you've had a look. It's anomaly detection on a fan to determine if it's clogged or not. So here we have ST evaluation board with a motor control on top of it. And we look at the input current for the motor behind the fan. And we really look at slices of this current input. So let's say, for example, a 100 millisecond slice. And we use this slice for learning and then for inference. So here the learning really happens on the microcontroller from scratch. So here it's programmed in a very simple way. First of all, you reset everything. Then there's an initial learning phase of a few iterations, let's say 50 iterations. And then when it's done, you switch to inference and do inference forever to check if what you're seeing looks like what you've learned or not. And the output is a similarity percentage, so 100% when it's similar and close to 0 when it's not. So now the learning is over, we can start clogging the filter a little bit, and we see that the percentage of similarity drops a bit, which means that here the clogging percentage increases a bit. And if we put another layer, it clogs a bit more, and so on and so forth. And of course, when we remove the clogging, it goes back to normal. But what is not shown here, and what is very exciting, is that you could learn something completely different. So with the exact same library, you could just completely clog the fan and relearn from scratch. And then it will consider that this fully clogged fan is normal. And then when you remove the clogging, then it will be abnormal, of course. So it's very, very adaptable. Okay, so let's quickly skip through that. Here's another demo that looks a bit like it. But here we're combining anomaly detection and classification, because sometimes it's not enough to just say, oh, there's an anomaly. You also want to try to classify this anomaly. So on a fan, it could be, I don't know, some obstruction. That could be one class. It could be some misalignment of the blades. It could be maybe different speeds of the fan also that you would like to classify. It could be also someone tampering with the blades. So here, whenever an anomaly is detected, we take this same input buffer, so this slice of input current, and we pass it to the classification library. Here, there's quite a big difference between anomaly detection and classification, the way we do it. Again, anomaly detection is a dynamic model that learns from scratch within a microcontroller, whereas classification is a static model. So you need to provide data representing all your input classes, or output classes. So here we learned the normal behavior of the motor, of the fan, and when we clog it, not only does it say error, but also clogged. So we did anomaly detection and classification. So now back to normal, and we'll introduce another type of anomaly. Here just friction on the blades. And now it says error friction. So we can classify. Okay, so I'll skip the rest. And how is it implemented in the code? Basically, when you get this library out of NanoEdge AI Studio, you get 3 simple functions to learn, to use. Initialization, learning, and inference or detection. So initialization, you know, reset the knowledge, reset the model. Learning, so here it's very, very, very simple. You just do a few loops of learning, get fresh data. So here just an accelerometer, like 3-axis accelerometer data. And then you use this data as input for the learning. And then it will update the knowledge 15 times. And you can print that the process is over and move to inference, in which case you do an infinite loop, for example. You could do many different things. You get fresh accelerometer data, and then instead of passing the accelerometer buffer into the learning function, now you pass it to the detect function, and the output is a similarity percentage, and you can place a threshold on the similarity to make decisions. So here, simple thing, we consider that above 90% it's normal, and under 90% it's abnormal. But again, it's a very simple example, and you could imagine some much more complicated logic. Okay, so now let's dive into some use cases for that. So this is one of the first use cases for NanoEdge. Even before NanoEdge AI Studio existed, NKE Wateco had a smart no, it was not smart. It was just a movement detector. So a box with an accelerometer inside, and it was able to detect shocks and movements and so on. And they wanted to bring, some more intelligence there, something that could learn and that could, do a bit more. So what they did is take an AI library, an NanoEdge AI library, put it inside. It didn't change anything about the hardware, just changed the code a little bit to do exactly what I described, to the learning and the inference by the push of a button. And here, actually, you could, by pressing this button, update the knowledge. So instead of running an initial learning phase followed by infinite inference, you could do additional learning phases. For example, you stick it on a machine, and then it runs normally for a while, but then you've got another regime appearing that starts giving off anomalies. But you would like to consider them as normal. So you press the button, it learns this new behavior as normal, and then you resume your detection. So basically, by doing that, they multiplied the selling price for this by like 15. So it used to be 50 euros, and then it was like 700 plus. Approximately the same use case, but instead of using just vibration, this one uses a combination of many different sensor inputs, like humidity, sound, vibration, gyroscope, temperature, gas, and so on. So you can do data logging with that. And you see that they also made a little phone app to link with the device. So all these things like phone app or communication, it's outside of the scope of the library. But of course, you can build all the features that you need using our very simple building blocks. Predictive maintenance for electrical solutions. So this one was for a smart breaker, an industrial smart breaker, where when there's a surge in current, it needs to be cut, but very, very quickly. And these parts, it's like an explosion. It's very violent, it's like boom. And so it ages quite fast. So they needed to know when to change their parts, not too soon, not too late, exactly at the right point. So they did that with an accelerometer. And here, presence detection with a time of flight, I think, stuck to the ceiling. Okay, electrical arc detection as well. If you look at the input and output currents and voltages for your batteries, you can collect data and try to look for anomalies using the exact same process. And here, the microcontroller is a U5, so it's a ultra-low power microcontroller. And you see that, well, here the flash and RAM requirements for these libraries, I would say, are quite high. 11 kilobytes, 29 kilobytes of RAM and flash, respectively. But typically, the sizes that you get are more about 2 to 5 kilobytes. So they easily fit into the smallest microcontrollers like G0, F0, and so on. Filter clogging. Okay. So here's a video, but I think it's a bit too long and too boring, so I will just show screenshots. I don't know how well you can see that. So this is what the studio looks like, and the pipeline is quite simple. First, step number 1, project settings. You define your input signal. So here in terms of number of variables, this is an example for a 3-axis accelerometer. So of course I have 3 variables. I put 3 here. I select my board. This one is a ST-Win that has many industrial grade sensors on it and also wireless capabilities. Then you input some data. And here we're not talking about hundreds of thousands of data points. It's more about 100. Or 50 or a couple of hundreds, depending on what you want to achieve, right? If you want to solve a very complex issue, maybe you need more granularity in your input data. So here we have 100 signal examples. So you see these are temporal slices of the vibration on 3 axes. And you have some FFT as well. So you import some examples of normal signals, also some examples of abnormal signals, just for context. Again, here we're not learning anything. We're not training the model. We're just trying to figure out if it needs to be a decision tree, or if it needs to be SVM, or if it needs to be some kind of neural network. And also if it needs FFT or not, or if it needs reframing or standardization or not. And it all happens during this benchmark process. And here the studio is very pragmatic. Whenever something works, then it's kept right in the pipeline. And if it yields worse results, then we throw it away and look for something better. So after 10 minutes, 15 minutes to 1 hour or a couple of hours, you will find the best solution and test this best solution with the emulator. So maybe it's a bit tedious to compile the code, flash it to a microcontroller, and put this microcontroller on the field. So instead, here you can directly test the library without any more effort. And if it works well, so the next step is validation. So here you have a summary of all the metrics and so on. So if it works well, then you can move to deployment. But if it doesn't work well enough, you can go back to steps 2 and 3 and change something in your input data. So there's many things you can tune, right? There's the type of sensor, there's the positioning of the sensor, there's the sampling rate, there's the sensitivity, maybe you need a combination of several sensors, or, you know. So adapt, like change something, try again, and iteratively like that, you will quickly converge to the best possible solution. Or maybe it is a problem that is too complex and there's no viable solution, in which way you will also see it from this benchmark results. Here, 87, 89%, 88% is okay, but probably not best, depending on the level of false positives, false negatives that you want to achieve in the end. And then deploy that on the MCU and go to production. So I already showed that. Okay. So a few mentions about the updates of the new version. So now you can even do data logging without writing any code. So you can select the board that you want to use, drag and drop the binary, and have a data logger ready to go. And it will log in USB, so it will output the data in USB, and you can use that as input for the studio. So really, in a matter of minutes, you can have data ready and a benchmark already running. Data manipulation. So on the contrary, if you already have data that is usually formatted as big columns that are very long on many different sensors, if you've got headers, you've got timestamps, usually like the way we did it a few months ago for some customers is write Python scripts. Here you can do it again with no code. You can drag and drop your files, remove columns, transform big columns into buffers, and so on. And finally, the one that I showed you already is the benchmark report generator. So if you want to share your benchmark results with anyone from your team, just export to PDF. And it also gives more transparency with regards to the contents of the library, because this is a problem that we often face in machine learning, the lack of transparency. Here, this doesn't remove the fact that some models will never be explainable. So you know that they work well, but you're not quite sure why, and you can never be sure that they make the right decision for the right reasons, right? But still, here we provide as much as we can, like the exact contents of your machine learning library. So here there's STFFT, followed by average sliding windows, followed by absolute value, and that goes as input into the model that is here ZSM, which is one of those which we developed and patented. Okay, so just a final slide, okay. Just a summary about the key benefits of NanoEdge here, mainly no AI skills, quick pipeline, sensor agnostic, frugal, optimized for MCUs, and no cloud dependency. It doesn't mean that the cloud is not useful, right? Many valid applications require the cloud, and it's an incredible tool to have. But if you choose to not use the cloud, now with this, I believe you can. So depending on what you want to achieve, it's really great. Okay, so I think I've reached 30 minutes. So I can skip the rest and maybe we can move to questions. Yes?
It's compatible with any of the STM32.
Yes.
Is there anything in the tool which can, for instance, estimate the percentage of the MIPS and stuff like that of any particular device, such that you could select the optimum device?
The percentage of what, sorry?
Let's say the CPU cycles that are being used. You want to use other stuff as well as just this.
Yeah, so that's a feature that is much requested, and we're working on it at the moment, on trying to estimate the execution time, right, for any given microcontroller. Yeah. So this is something that, again, is will be very useful, especially for some applications like motor control and things like that. So there's different ways to emulate these microcontrollers and how the libraries behave on these microcontrollers. But so far, it has proven not to be so reliable. But now I think we've found a way to make it happen. So probably in the very near future, we'll have an update with that. But this is something that we're working on, definitely. Yes. Yes.
Hi. How does the royalty work? And I know it may sound a silly question, but why would there be a royalty if it's if we're not using like a continuous service like all the time, like not reserving a cloud space or something like this?
Sure. So just to iterate quickly on the business model, so the studio that I presented today is available for free. You can download it on ST website, and then you can test it for free as well. There's, as you mentioned, a little royalty when you go to production. So when you found the library that works, you can deploy it on the field, and there's a little cost associated, depending on the volume. And this is because really it provides a lot of additional value, and even sometimes, depending on what you want to do, you can save on other things. So you can remove some things from your BOM and replace them, depending on the case, with some machine learning features. For example, replacing a sensor, right? You've got, let's say, 3 sensors. You can use 2 to predict the third one. Yeah, that's one possibility. And also, I think it brings, depending on what you want to achieve, it's very difficult to give a general answer, but it provides a lot of value, and you can gain so much time on the development cost and on the like the expertise that you don't need in machine learning, that you can, all this time and effort, you can focus them on something else, maybe on brainstorming new use cases, and so I think this justifies a little extra cost.
So is that one-off payment per every time you embed that AI into every microcontroller?
So yes, this is not related to the libraries, but to the number of devices deployed, because you can easily put several libraries on the same microcontroller.
Sure.
But let's say you put into production 10,000 devices, so there will be the volume will be 10,000, regardless of the other of the number of libraries and so on.
Thank you.
Yes.
Do you have any product that like scans people's faces and marks them as present in a system?
Yes, we can achieve something like that, not with NanoEdge, because as I said, the applications like image or speech, typically there's better ways to do it with the traditional approach, so neural networks typically. So you will see at the ST booth, we have a demo with that. That looks pretty much like what you described with a camera. And here the use case is detecting how many people are in a given frame. So we not only detect the face, but the whole body, and we count the people. But on another event previously, I've seen a demo where we do exactly that. So we look at the face of one person, then we click a button, and this person now is part of the VIP list or whatever. So is inside the system, and now it's recognized. From now on, this person will be recognized. So whenever he enters the field, like you can display a name or, on top of his head and so on. So yes, recognizing one person's face in particular and adding them to a database. It's definitely possible.
Thank you.
Thank you.
Hi.
Hello.
Regarding the embedded devices, like lots of focus is also around power consumption, let's say. Would you think that this technology could also be used on battery-powered sensors or like devices?
Of course, of course. So you could either try to use the machine learning itself directly on the outputs of the battery to improve the lifetime of the battery, do that directly, or you could do it by tweaking the way you use the machine learning features in your final code. So, and especially if you use a very low power microcontroller, usually you want to stay in sleep mode for as long as possible and then only wake up to do something useful. So for example, if I go back to this Bob Assistant, one of the first devices developed, it was not doing continuous monitoring for weeks, right? So it did, it slept most of the time and then woke up every 10 minutes to do one little iteration of inference. Then if it sees nominal state, it goes back to sleep for the next 10 minutes. Otherwise, if it sees something weird, for the next minute, it will do many more inferences, like every 10 seconds or something. So it will try to confirm if there's something weird going on, if there's a real anomaly or not. And if there is, blink a LED or send a message to a remote dashboard or whatever, and then go back to sleep. So indeed, you can do it with the AI itself, or by just being a bit clever in the final code and spending as much time as possible sleeping, which is probably the preferred way to do it, which you can pretty much always do.
Yeah, for this dynamic model situation, is it straightforward to extract and update the weights in the model? For example, if you have a device which is, you just want to see how the model is performing and you want to run that in the emulator or run it offline, are those weights like accessible within the code that you can then send them somewhere? And then the same if you have multiple devices, one of them is trained well, let's say, and you want to apply that weight across your fleet, can you do the same sort of thing? Like, is that straightforward in the system you've got at the moment?
Thank you. So yes and no. No, because it's not weights like you would imagine in a neural network, right? So it's much more general than that. You can have just decision trees or SVM or any other machine learning model. So in that sense, no. But really, what the knowledge is just a bunch of numerical values somewhere in RAM. So you can extract these weights or this table in C language and extract them, put them somewhere in the flash memory, and transfer it to another device that has the same library to bring this knowledge that was learned on another device into this new device. So there's ways to do that, and we have a tutorial to do that as well on st.com. Thanks. Okay, no more questions. So I will thank you very much for your attention and have a very nice evening.